So we're going to start out introducing these rational functions. A rational function just means you have both the numerator and denominator of polynomials. Like here's an example. You have that 2x minus 12 is a linear function, right? It's a linear binomial, polynomial there. On the bottom we have also another linear x plus 2, right? So it's just a polynomial over some other polynomial. And what we're going to do initially is we're going to just practice making sure we know how to find our x-intercepts. Remember, if you find an x-intercept, you got to let y be 0. On the other hand, if you're finding a y-intercept, you got to let x be 0. So let's find the x-intercept first by letting y be 0. So here's our function. We're going to let y be 0. So think about this for a rational function. If y is 0, the only way to make this true is if my numerator is 0. Because 0 divided by anything, right? If that red stuff is 0, 0 divided by anything is 0. So that'll be a true statement. So when you're finding the x-intercept, you just got to take the numerator, say it equals 0, add 12 to both sides, divide by 12, and you get 6. Right? So it's saying this function has this point 6, 0. Right? Whoops, right there. There's our x-intercept. Let's go ahead and find our y-intercept. When you're finding the y-intercept, we're going to let x be 0. So you end up with 0 minus 12. I get a negative 12 over 0 plus 2 is 2. So negative 6. So 0, negative 6. Right? So it goes through those 2 points. And we'll talk about kind of what this thing looks like later a little bit more as we're getting into more of these properties. But these rational functions, they have asymptotes, okay? And the way that you find the vertical asymptotes are anywhere where the rational function is not defined. And so what we're going to do is, we know we can't divide by 0, so we're going to set our denominator equal to 0 to find a vertical asymptote. A horizontal asymptote, so in this case, the one that's pictured, it has a vertical asymptote right down the middle. It's never going to touch x equals 0. It'll never touch that. In fact, this is the equation for y equals 1 over x. So to find the vertical asymptote, what you do is you take that denominator, say it equals 0. That's the equation for that vertical line, that imaginary vertical line, x equals 0. The horizontal asymptote has some rules to find that. The definition of a horizontal asymptote, it says that as I take n to infinity or to negative infinity, in other words, it increases in magnitude, if the rational function approaches a y value, then I have a horizontal asymptote at that y value, at that functional value. Okay, so there's some rules for it. And here's the rules for the horizontal asymptote. So if, number 1, if the degree of the top n is less than m, that's number 1 right here, then y equals 0 is automatically your horizontal asymptote. Okay, for example, y equals 1 over x. The degree of the top, I know x is not listed, but that's a 0 degree. The degree of the top is 0, the degree of the bottom is 1. 0 is less than 1. So automatically, the horizontal asymptote is y equals 0. That's this one pictured right up here. Here's the green line, horizontal line, y equals 0. Okay, so it has a horizontal asymptote, y equals 0. Now the second rule says, if they're equal, number 2, if they're equal, like let me give you an example. Like let's say I have 2x squared minus 3x, blah, 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 who cares about the rest, over 3x squared plus 7. Okay? See how the degree of the top is the same as the bottom? If that's the case, as x goes to infinity, it's going to approach the leading coefficients. Y equals 2/3 in this case. So the horizontal asymptote for this would be the leading coefficients. Why? Because the degrees are the same. So that's number 2. If the degrees are the same, take the leading coefficients. Make sure it's written in standard form first. And finally, the last scenario is if the degree of the top is greater than the bottom. So like, for example, 3x to the 5th minus 2x plus 1 or whatever. and the bottom is x to the 4th plus 17. Degree of the top, bigger than the bottom. Guess what? No horizontal asymptote. Now, if it's only 1 degree more, if it's only 1 degree larger, in this case it is 5 to 4, there's only a difference of 1 degree, right? Then I will have what's called an oblique asymptote, and we'll talk about this later. This is an example of an oblique asymptote. So as the x value shoots out, it gets closer and closer to that line, that slant asymptote. Oblique asymptote is the same thing as a slant asymptote. But let's go ahead and find our vertical and horizontal asymptotes for this one, for the one we already found the intercepts for. So y equals 2x minus 12 over x plus 2. Number one, where is this thing undefined? Where do I have a vertical asymptote? Well, I can't divide by 0, so I take my denominator, set equals 0, and I say that's the equation for my vertical asymptote. I will not touch x equaling -2. Right? They'll never touch that line. I can't. That's where it's undefined. The horizontal asymptote, I say, well, what's the degree of the top? X to the 1, right? Degree of the bottom? 1. If they're the same, n equals m, right? In this case, 1 equaling 1, they're the same. Then what do? Well, the horizontal asymptote is the leading coefficients. 2 over the number in front of that x is 1. So y equals 2. Y equals 2, right? Now, this is actually the one that we had 6, 0, -6, 0. I mean, if you plotted a few more points, you could kind of graph this thing, so it kind of looked like that. But we're not asked to graph on this one. We'll do some more graphing later. But those are the asymptotes for it, the vertical and the horizontal. Let's do some more with a picture this time. Let's identify number one. I'm going to actually identify the vertical asymptotes here. So what are your vertical asymptotes? You see this first vertical line in red? X equals -6, right? The other one's a little hard to see, but that's actually at x equals a half. So I have 2 vertical asymptotes. It'll never touch that. That's the giveaway for my domain. My domain will be everything except those values. So it'll come from -infinity up to -6, but it'll never touch that vertical line. Then it'll be all defined in between there. You can see the blue there. It's all defined. And then it'll have another break at 1/2, right? Let me just erase that junk. So my domain stems from the vertical asymptotes. Will be defined between them, then it'll take off again after a half. Okay. Now the horizontal asymptote, can you see in blue here, as I move out, oops, what happened to it? No. Try that again. Oh my gosh, what's wrong with this thing? Okay, there we go. As I move out, as x gets increasingly large, see how it gets closer and closer? It's going down a little lower, very close to this horizontal asymptote of y equals 0. That's where my horizontal asymptote is. It actually gets closer and closer to it. Interestingly enough, though, you can cross the horizontal asymptote. See that point right there? -3, 0? It actually hits it. So you can cross a horizontal asymptote. In this case, it does. The definition of a horizontal asymptote just says, as I look at the extremities, as x goes to infinity or -infinity, is it approaching a y value, right? In this case, you can see that it is in the graph, okay? There's no slant or oblique asymptotes. That doesn't apply. Let's go ahead and talk about the range, see how it's all defined from -infinity Oftentimes it doesn't hit the horizontal asymptote. In this case it does, so it goes right through it and keeps going. So your range is all real numbers for this one. Okay. All right, let's go ahead and find our intercepts, and both the x-intercept by letting y be 0, our y-intercept by letting x be 0, and then let's go to our vertical asymptotes after that as well. So let's do our x-intercept first. Let y be 0. Well, to be true, the numerator's got to be 0, right? Add x squared to both sides, square root. So I got plus or minus 1. So this will, again, I know you're not graphing, but who cares? We'll just throw it on there. It's going to hit here. It's going to hit here, right? Plus or minus 1. Now let's find our y-intercept. Let's let x be 0. So it looks like I got 1 minus 0 over 0 minus 0 plus 6. So I got y equals 1/6. So 0, 1/6. So it hits about right there. Our vertical asymptote comes from the denominator. Where is this undefined? Well, anywhere I can't divide by 0. So this stuff on the bottom can't be 0. Well, that's not factored. So factor it. There's my two equations, x equals 2 and x equals 3. X equals 2, there's one of my vertical asymptotes. X equals 3, there's my other vertical asymptote. Now the horizontal asymptote on this, notice the degree of the top, and I'm going to write this in standard form. Instead of 1 minus x squared, I really should have that as negative x squared plus 1. So notice degree of the top is 2. If they're the same, right? They're the same, 2 equals 2. Take the leading coefficient. The horizontal asymptote will then be negative 1 over positive 1. So the horizontal asymptote is negative 1. There's my y equals negative 1. My domain is just interrupted by my vertical asymptotes. The vertical asymptotes was 2 and 3. It'll never be 2 or 3. So it'll go from negative infinity up to 2. And then it'll go in between them. It'll also be defined. And they'll take off after 3. Okay, oops, I don't need to circle that. Okay, let's do that similarly on this one. This one wouldn't be a bad one if you want to pause and try this one as well. More than welcome to. Let's find our x-intercepts by letting y be 0. Means the numerator's got to be 0. So x equaling 0 or x equaling 3. My potential x-intercepts. But notice, well, I'll get to that in just a second. Let's go ahead and find our y-intercept here by letting x be 0. Notice I got 0 over 0. We can't divide by 0. No can do. So there is no y-intercept, right? In other words, it's not hitting at 0, 0. So this point's not even part of it. It will hit at 3, 0. But it's not going to hit at 0, 0, right? And we can verify that also with our vertical asymptote. Vertical asymptote is, where is this thing undefined? Well, if my denominator is 0, I have an issue. Let's go ahead and take a 2x squared out. So I have 2x squared equals 0. So divide by 2 divided by 2, x squared equals 0, divide square root, plus or minus 0. And then this 1 plus 2x factor equals 0. Minus 1, divide by 2, divide by 2. So 0 and negative a half, x equals 0 right down the middle, and x equaling negative a half as well as my other vertical asymptote. Horizontal asymptote. Well, the degree of the top, again, let me make sure this is in standard form. I got x squared minus 3x. Here I should have had a 4x cubed first, plus 2x squared. Degree of the top is 2. Degree of the bottom is 3. If the degree of the top is less than the bottom, automatically, here we have 2 less than 3, automatically y equals 0 will be our horizontal asymptote, y equals 0. And the reason is, you guys, is as x gets big, as x gets increasingly large, the denominator, because it's being taken to a power more than the numerator, will be so much bigger than the numerator. So we're essentially dividing by this huge number. As x gets increasingly large, we get closer and closer to 0, right? That's why if the degree of the top is less than the bottom, you're going to approach y equals 0. The denominator will get so much bigger than the numerator, okay? All right, a few more here. And this one, the nice thing about this one is we'll have an oblique asymptote on this one. Let's go ahead and find the vertical asymptote. Where is this thing? Undefined. Can't divide by 0, so x equals -2. Right? Not going to touch x equals -2. The degree of the top is 2. Degree of the bottom is 1. So n is greater than m. So there's automatically no horizontal asymptote. Now, since the degree of the top is only 1 more than the bottom, it's only a difference of 1 here, then we have an oblique, or slant, is also referred to as a slant asymptote. And the way to find that is you got to do the division. So right now we have this 3x squared plus 10x plus 6. It's being divided by x plus 2. So we're going to go to the side, and we're going to go ahead and do the division, long division. We're going to write this as quotient plus remainder over divisor. So let's go ahead and do this. X goes into 3x squared, 3x times, go ahead and multiply it through, 3x squared plus 6x. Don't forget to change your signs. So we have 10x minus 6 is 4x plus 6. Now I'm matching the 4x. What times x gives me 4x? 4 does. 4 times x, 4x. 4 times 2, 8. Don't forget to change those signs. And we got a remainder of -2. So in other words, this is quotient, 3x plus 4, plus remainder over that divisor, x plus 2. Now what happens as x goes to infinity, this part goes to 0. This is going to go to 0 because the denominator gets so big. Because I have -2 over some huge number. So that's going to 0. So what I'm left with is this. That's my oblique asymptote right there. It's my quotient. Okay, so my oblique or slant asymptote is y equals that. Y equals 3x plus 4. Okay, y equals 3x plus 4. In other words, it's this line, and as it goes out, it's going to get closer to it. I don't know what the points are, but as I shoot to infinity, I'm going to get closer and closer to that slant asymptote. Okay. Now let's do a little bit of transformations with these now. So this first one, let's talk about y equals 1 over x for a minute. Y equals 1 over x. The vertical asymptote is x equals 0. See it right down the middle, right? And then the degree of the top, this is x to the 0. Anything is 0 is 1, right? Is 0. The degree of the bottom is 1. So n is less than m. So automatically it's y equaling 0. I'm going to put in green. And then you could graph a whole bunch of functions, and or a whole bunch of values, and you'd see the graph in black there, right? So there's y equals 1 over x. Kind of get that ingrained in your head. 1 over x squared again, the vertical asymptote would be Where is this equals 0? So x times x equals 0, x equals 0. Also has the same vertical asymptote. Degree of the top is 0. Degree of the bottom is 2. So it automatically also has y equals 0. And then you plot a bunch of points for that one. You know, like 1 squared 1, 2 squared. You'd have 1 over 2 squared, 1/4, and so on. Negative 1 squared, those positive 1. So you got 1 over positive 1. And you get that graph 1 over x squared, right? Which is, you notice it's reflective and about that y-axis, right? The right-hand side matches the left-hand side if it's reflected about the y-axis. Kind of a mirror image there. Well, these transformations of these two can be helpful. For example, this y equals 1 over x plus 1 over x minus 3. So it's similar to y equaling 1 over x, right? We know 1 over x kind of looks like this. So then the question is, well, what does that minus 3 do that's inside of the function, if you will? Which way is that going to move it? Right or left? That'll move it. That's a horizontal shift right 3, actually. So it's what it's going to look like is it's going to be similar, but it's shifted over 3. Okay. Again, if you're not sure, well, let's just go through the vertical asymptote. Where's this thing undefined? At x equals 3. I'm going to have a vertical asymptote at x equals 3. And then after that, I could just plot a bunch of points. You know, I have a vertical asymptote at 3, so don't worry about that. But let's go to the right of it. Let's go to the left of it, and so on. And you could plot some points, and you'd soon see something like that. Right? It looks a lot like that original, and I didn't even do the horizontal asymptote yet. Horizontal asymptote, degree of the top is 0, degree of the bottom is 1. So it's automatically y equals 0, right? You kind of have a feel for that with your transformations. So transformations kind of help you out with that, right? Now this one, it's not factored. Let's go ahead and factor the denominator there. So I got negative 1 over x plus 3. In other words, negative 1 over x plus 3 squared. So I'm thinking to myself, well, this is similar to 1 over x squared, which we know looks like this, right? Well, what's the negative in front going to do? It's going to reflect it about the x-axis, right? So now, what would that do? Here's the negative in front. Now I flip that over, and I'm like this, right? And then what does the plus 3 inside of it do? Right or left? Left. Good. So that's left 3. So now it's like this. That's kind of what this thing looks like. Let's go ahead and think about this in terms of vertical asymptote. The vertical asymptote, where does x plus 3 equals 0? X equals negative 3. 1, 2, 3. Put the vertical asymptote on there. For the horizontal asymptote, I'm thinking about this in this standard form. Degree of the top is 0. Degree of the bottom is 2. So automatically, since n degree of the top is less than the bottom, automatically y equals 0, right? And again, plot some points to kind of see the rest of that. To be a little more exact, plug some points in. You kind of get the feel with it with transformations. All right, this one's kind of interesting. Before I think about this with transformations, I would say, well, that x on the bottom is a common denominator. So this is same thing as x over x minus 1 over x. In other words, 1 minus 1 over x. In other words, negative 1 over x plus 1. Now I'm getting somewhere. So this is similar to 1 over x. So I'm like, okay, here's my 1 over x. But I have a negative in front. So that's going to reflect it about the y-axis. So now I flip it about the y-axis. There's the negative 1 over x. And then how about that plus 1 outside of it? What's that going to do? Up 1. Up 1. Now bump that. Yep, bump that red one up 1. So now we have negative 1 over x plus 1. So that's up, vertical shift up 1. So the whole thing goes up 1, but it looks like the red. So there's the transformations. Now let's answer a few questions from the original. I like to start with my vertical asymptote. My vertical asymptote from the original, x equaling 0. So I'm like, okay, I'm not going to touch x equals 0. Let's go to the horizontal asymptote. Well, the degree of the top is 1, the degree of the bottom is 1. They're the same. If they're the same, then we take the leading coefficients. Leading coefficients 1 over the number in front of x is 1. 1 over 1. So y equals 1 is our horizontal asymptote. The domain comes from our vertical asymptote. It'll be everything except 0. So we'll go from negative infinity up to 0. Then there'll be a break, and then it'll take off again after 0. And again, we should plot some points on this, you know. Ideally, you're plotting a few points, but you're going to kind of see this behave as we mentioned with the transformations. You're not going to touch that, in this case, you're not going to touch that red horizontal asymptote at y equals 1. So it'll be defined from negative infinity up to the horizontal asymptote, and then there's a break, and then it keeps going after that. So negative infinity up to the horizontal asymptote. It doesn't cross the horizontal asymptote in this case, and takes off again. There's no oblique asymptote on this one. And you can make this a u-try problem. I'm going to pause this, and you guys can go through and try this one as well. All right, let's do the transformations. So we got 4x squared over that common denominator minus 2 over x squared. So this is 4 minus 2 over x squared, but I'm going to write that as negative 2 over x squared plus 4. So this behaves like, kind of like y equals 1 over x squared, which we know looks like this. The 2 doesn't make a big difference, right? It's just going to kind of stretch that out a little bit. So similar to that. Now, I'm going to first address the negative. So what would this do? And I'll just put a 2 on it. Again, it doesn't, just stretches the points out a little bit. Reflection about the x-axis, right? So it flips it over. So far, so good. And then what does that plus 4 do? Up 4, good. So now it's like this kind of thing. So I didn't draw that very well. So we're like, oh, okay, now let's go through everything. Number 1, let's do the vertical asymptote from the original. Where is it undefined? X equals 0. Right down the center. Not going to touch x equaling 0. Can't divide by 0. Let's do the horizontal asymptote. The degree of the top is 2. Degree of the bottom is 2. If they're the same, what's our horizontal asymptote? Leading coefficients, right? 4 over 1. 1, 2, 3, 4. So here's our horizontal asymptote. In this case, we're actually not going to touch that. There's no oblique asymptote. Oblique asymptote's only if the degree of the top's 1 more than the bottom, right? That's the only time you have that slant or oblique asymptote. We'll talk more about those in subsequent sections. But let's go into the domain. Remember, it's not going to touch that red line at x equals 0. So the domain is going to be everything except 0. And then the range, and again, ideally you're graphing some points here, right? I know that's not very exact, but you're not going to touch the range. You're going to come from negative infinity up to that 4, but you're not going to touch the 4 on that. And that's it for the information for that rational function. Thanks for watching. See you guys next time.